Okay, so next up is definite integrals. So having looked at, I suppose, indefinite integrals and that idea of an antiderivative and anti-differentiation as kind of a whole concept, and we have that idea that for any function f of x, I can create this or kind of compute or calculate this integral, which is the reverse of differentiating it. So if I have the derivative, I can find the original function or a potential original function, and then I need more information than to find the exact version of that integral or the exact original function. Um, for the derivative that I'm given. Looking at, I suppose, a definite integral here. Now, when we're computing what we call definite integrals, that's going to require us to be given information about 2 points on the function. And usually it's just two x values, for example, where most of our functions tend to be in terms of x. So usually two x values, and we would call them an upper and a lower limit or bound on our integral, on our integration. So you can see here in the definition, the symbol or the kind of layout we would be looking for is what I'm kind of highlighting here in yellow. So we have the integral symbol, the little kind of S shape with the A and B. So A is your lower limit, B is your upper limit of your integration. And we're basically saying integrate this function between these 2 points and tell me what the value is going to be then between those 2 points. So we're essentially integrating the function to find f of x and then evaluating f of x at those 2 points of b and a and finding out the difference between the two there. Okay, because we are doing kind of two separate integrals, if we were to do our plus c and our plus c here, they would essentially just kind of get rid of each other. So when we're doing definite integrals, there's no need for the constant of integration. Because I suppose in the name, we're kind of more definite of our answers in this case. Now, this sort of idea of computing a definite integral is really, really important as we move through the rest of our integration, because really definite integrals are probably the most common type of integral you would have to compute. It's particularly used in area and calculating area under the curve or area between two curves. A lot of the time that's going to focus around those x values that we're setting as our upper and lower bound. So really, really is one that's worth just taking that little bit of extra time to work with. Really, beyond computing the values, there's actually nothing new to it. The actual process of integrating is exactly the same as we've kind of looked at in the previous video there. So evaluating the following integrals. So looking at the first one here, we're integrating 4x plus 1 dx, so relative to x. So first just compute the integral, so that's going to give me 4x squared over 2 plus x, and that needs to be evaluated at minus 1 and 2. Okay, so we can simplify that a little bit more, so maybe 2x squared plus x, and still evaluate at 2 and minus 1. So next I'm going to evaluate those, so I'll fill in 2 for x, and let me keep maybe to square brackets, and we'll do minus 1 as well for x. I'm going to work out both these values, so that's 4, 8, 10 minus, let's see, 2 minus 1, so minus 1. So minus 2 minus 1, so that's just 1, of course, minus 1 overall. And that gives me an answer of 9. So we're basically saying, yeah, for this 4x plus 1, the original function evaluated at 2 and minus 1 gives me an answer of 9. We can look at the same thing then for this next function here. So again, same as before, we'll evaluate or calculate the integral first. So 3x squared over 2 minus x to be evaluated at 1 and 3. So let's get going with that. So 2 times 3 cubed over 3 plus 3 times 3 squared over 2 minus 3, and then filling in 1 as well for our other option here. So let's fill in some of these values here now. So again, at this point, it's kind of just calculator work nearly more than anything else. Just kind of familiarizing ourselves with layout here somewhat also. For these questions. So that's going to give me, let me see, have we filled everything in? Oh, my minus 3 should be off the bracket there. 57 over 2. And changing all of those 3's now to 1's inside the brackets there. At the end, 7 over 6. That's going to give me an overall answer of, let me see, 57 over 2 minus 7 over 6, 82 over 3. Okay, 82 over 3 as my value there for my definite integral between those values of 3 and 1. And we'll see, as I say, in later sections, kind of a real practical meaning for that, and kind of looking at kind of how this integral is used and what it even represents in a kind of more geometric way, I suppose, or kind of looking at what it means for the function. But looking just purely at computing them in these ones, so we'll just do 2 more practice questions just to kind of see. Again, just getting familiarity with it at this point. So this one here, we're looking to evaluate again the integral first. So x to the power of 6 over 6 minus x to the power of 5 over 5 plus x to the power of 3 over 3. Sensing a trend here, minus x to the power of, sorry, excuse me, that's 4 over 4. And then minus x to the power of 3 over 3 plus x to the power of 2 over 2. Okay, real trend going on there. Evaluate at minus 2 and 3. Okay, so I'm going to fill out exactly what I'm going to be doing. Again, this is always just good practice. Okay, I know people kind of are probably looking and saying, right, we're writing down an awful lot of this. I could just fill this into my calculator at this point. You could, of course. I think it's never any harm to write down as much as possible when you're doing any sort of kind of mathematical sum. It's just going to ensure as much accuracy as we can. And I suppose if we're looking at kind of getting marks and things like that, having as much written down is just going to kind of help you in ensuring that you get as many marks as possible, and just account for any possible mistakes that could occur along the way. So let's fill in some of these values here now. So 3 to the power of 6 over 6 minus 3 to the power of 5 over 5 plus 3 to the power of 4 over 4 minus 3 to the power of 3 over 3 plus 3 squared over 2. And that's going to give me an answer of 1773 over 20. Okay, not the nicest answer, but they weren't the nicest numbers. We've 5 different fractions here, for which only a few of them really have any real nice common denominators. So maybe to be expected here. Just being careful here now, because I'm filling in a minus 2 or a negative 2, so I have to be careful, because I know straight away that if I'm not using brackets, my calculator may give me an incorrect answer here. So we just have to be very, very careful with the results from my calculator here. I'm noting as well, even looking at it for myself, well, everywhere that has a negative power, or everywhere, excuse me, that has a negative sign in front of the fraction also has an odd power. So therefore, when the minus 2 is raised to that power, my answer should be negative because it's an odd power, but then that negative in front of it should overall give me a positive. So I'm expecting an overall positive answer here, which is what I've gotten. I suppose also just even bearing in mind that maybe the positive numbers just outweigh the negative numbers in the calculation here. And we're getting 755 over 12. Okay, as I say, not the nicest answer, I suppose, but not our fault. Looking at the next one now, this just presents, I suppose, a different issue, if you like, for us here, in that we don't have a rule like the quotient rule for integration that we need to use in terms of leaving cert maths. There are, of course, rules that we can use, but we don't necessarily have one here. So what we need to do is look for common factors here. So looking for common factors, we might recognize that this is a sum of 2 cubes on top here. So this is a sum of 2 cubes. The bottom may be some sort of quadratic. Okay, again, we would need to look and see, is there a way of factorizing it there? But let's just see. We'll focus on the sum of 2 cubes. First of all, x cubed plus 27. Obviously, that's x cubed plus 3 cubed. Okay, bearing in mind for sum of 2 cubes, the first bracket will match the question. The second bracket will always be different to the question. And the last bracket is always positive. Okay, so just small things here that can kind of help us in remembering that little formula for sum of 2 cubes. So first bracket's always the same as the question, second is always different, and final is always positive. Okay, I'm feeling happy now because looking at this here before I've even done any work on the bottom to see if it is a quadratic, I can actually see that I've actually saved myself that work here. So x cubed plus 27 over x squared minus 3x plus 9 is the same as x plus 3 times x squared minus 3x plus 9 over x squared minus 3x plus 9. So the quadratic term or expression that I have on the bottom of my fraction there on the denominator is actually a common factor of the top as well. So I can actually reduce that fraction down to simply x plus 3, which is much, much nicer for us when it comes to our integration here. So we are now integrating between 1 and 4 the function x plus 3 with respect to x here. So that's going to be x squared over 2 plus 3x evaluated at 1 and 4. So starting off here, 4 squared over 2 plus 3 times 4 minus 1 squared over 2 plus 3 times 1. And that's going to give me an answer of what? Now we probably could do some of these calculations without the calculator, but we'll just stick with it for the moment. So 20, and changing these 4's then to 1's, 7 over 2. Which is 33 over 2. Okay, so you can see here, following the same skills really, or the same methods that we've been using the entire time here. The method for integrating obviously isn't changing, but just that idea of definite integral. For calculating an integral between an upper and a lower bound, we compute the integral and then we compute the function at those two values. We calculate the value, or we evaluate the function at those two values, and that will give us what we call the definite integral.